Hello and welcome to the third video of this DSA problem solving series. Today we are going to start with linked list. Hope you enjoy. So let us have a look at the question here. The question says, the title of the question is populating next right pointers in each node. So let's read it. Let's give it a read. You're given a perfect binary tree where all leaves are on the same level and each parent has two children. The binary tree has the following definition. Just by the way, this is important that each parent has two children. So let's see the structure of our node. So it has a value, it has a left pointer, a right pointer, and a next pointer. We have to populate each next pointer to the point to point to its next right node. If there is no next right node, the next pointer should be set to none. Initially, all the pointers are set to none, and then we have been given the things as an example. So let us just hop over to our board. Uh, because we have to understand this problem because it is a bit tricky. So let's first understand the problem a little bit. So let's say this is our perfect binary tree. This is a balanced perfect binary tree. So let's see what the initial situation is because initially we have been given the constraint that everything is set to null. So the next pointer to this is set to null, and so on. But let us first understand what is the next pointer, what is a right pointer, and what is a left pointer, because that's basically that will give away the question. So for a root node, the left pointer will be this node. The left of this will be pointing to this, and the right of this will be pointing to this. Now, likewise, the right of this will be pointing to this. Wrong, completely wrong. The right of this is this, left of this is this. The next of this node is this node, which we have to establish because that's the question. We have to set the next of each of these nodes. The next pointer we have to set to the next node of the thing. So likewise, let us just see the next of this is this, this, and the next of 7 is it is none. So is this, so is this. So that was one important thing in this question is to distinguish between the left pointer, the right pointer, and the null pointer. And then let's see one more time what this question is telling us to do. After that, we'll jump on to the approach. So we have to set the next pointers, and this is how we have to set them. Null, 2's mix is 3, 3's mix is null, 4's mix is 5, 5, 6, 6, 6 is 7, and 7 is null. Okay. So this is what we want to do. This is what we have to return. So let us think of the approaches, how we can do that. This is the root node here, right? So what do we need to do? The left of this root should point to the right of this node root. Why is it so simple? Because then this point, this node itself becomes root. Itself becomes parent of two nodes, and then obviously so on can be done. So what we need to do is we need to take this as root first, then it's left as root, then it's right as root, and so on. It's left as root, root. Each of these elements we have to take as roots. Till when? Till when the left and right both are equal to none. If there is no, so the root condition or the base condition will be that it's null. And why am I saying that we have to have a base condition? Because from this pattern, we can realize that we'll have to make a recursive function. Because this is root, then both of its children are root, and then so on and so on and so on. So we'll have to have a recursive function in this. So let us have a look at our approach, how we can construct a recursive function. So let's say this is our recursive function. I think it's called connect in the problem. I've just written. Let's write connect. Why not? Okay, let's do it. So the base condition is if we pass root in this. So if root equals null, we have to return null, right? This is our base condition. Now what do we need to do? What are the conditions? Let's have a look at that. Code won't be too big. So if I should make the tree here. Okay, I hope this should be enough. Okay. So if roots left is not equal to null, what should we do? This is the root. We have come here. I need a bit more. I need a bit more children than the required. So yeah, here we go. So if roots left is equals to null, is not equals to null, what should we do? Its next should be what? Roots right. So roots left next should become right. Correct? But this is not where the conditions will end. So obviously this is all incorrect, but for the keeping the constraint of the length of board in mind, we'll start over. So those two conditions again, if root right is not equal to null, what should we do? Then if roots right is not equal to null, this is roots right, right? If this is the root, this will become right. What should we do? We have to connect it with this. So bear with me. Roots right next. Roots right next should be equal to roots next left. Roots next left. This thing. Roots right next. This thing. So we're talking about this. Roots next left. Simple as that. Right? Understood? And then there is one more important condition which in this loop which we have to take in mind. Let's take this parent. I'll read why. It's it just got a bit too messy there. Let's take this as the other parent. Let's take this node as our parent, alright? Let's take this node as our parent. So the code works perfectly fine. Roots rights next should be equal to roots next, because this we've already established. Roots next left. This works perfectly fine, right? So this can work anywhere. Well wrong. Because if this is the root node, let's take for an example, if this is the root node, then let's try to implement this roots rights next. Well, there is no next. There is no next. This next will become equal to roots lefts, roots next left. Then there is no left. Root has no left. How can we take roots next left when root has no next? So we need to add one more condition to this constraint, which is roots next should also not be null. And then finally, we'll call this function recursively for both the nodes, both the children nodes, which we'll see in the code. So let's just jump over to our code, share my screen. So let's begin writing a solution here. As we said, our first condition, if you remember what we wrote in the code, the root condition is that if the root itself is equal to null, what should we do? Well, we should return null. Okay, fair enough. What was the other condition? If roots left is not equal to null, what should we do here? Roots left right becomes roots right? Then another condition, if moves right is not, sorry, is not equals null and moves next is not equal to null, right? Next comes moves next left. And then, as I said, we have to call the function recursively as well. So here's how we do it. Connect. And then finally, what do we return? We return root. That's what they have asked for. Let's see if this runs in the initial test case. There is an error which we have to figure out on line number 33. So it really was a very silly mistake and took me way more time than I'd like to admit. It was next. We did, uh, we did solve it correctly on the board, but somehow missed it. So the initial test case is accepted and then the final one is also accepted. In speed, this is a fairly fast code and memory usage is also fairly decent. So do let me know what your solution to the problem was. Are there other methods? Is recursive method the best method, or are there better iterative methods as well? You can take the help of discuss as well. So thank you so much. That was all for this video.